So thank you everybody for being here. I will now present our first speaker that is going to present one of our ongoing projects called DASH. Dr. Sipel has been working with us for over 2 years now. And before coming to ETH Zürich and work with Professor Reto and Professor Nuti Reto and Nicola Mine-Townsend, he did a PhD in the Max Planck Institute for Biogeochemistry, and before that he had a master in science in Oxford University in environmental science. So Sebastian, thank you for sharing this with us, and please share your screen and talk to us about DASH. Thank you.
Yeah, thank you very much for the introduction. It's a pleasure to have this opportunity to give a talk today in this setting. It's also nice to see that so many people are interested. Yeah, the title of my talk and the project I'm presenting is Data Science Informed Attribution of Changes in the Hydrological Cycle. The abbreviation is DASH. And it's, as Fernando already said, it's a joint project from the first call. So we have been working on this scientific topic for 2 years now. And I should really say, this is very much a collaborative effort. And so I would like to say, well, these are all collaborators. So Reto Knotti and Nikolai Meinshausen are both professors at ETH for climate physics and statistics, respectively. And then our two senior scientists from the SDSC, Guillaume Obuchinsky and Eniko Sekeli, and myself. And the outline of my talk is the following. So it will be about a 15-minute talk and a few minutes for questions. So I would like to first present kind of the key science questions of the DASH project and the two topics that we mostly have been working on broadly. So the first big topic we've been working on is about uncovering regional climate signals using statistical learning. And the second big topic we've been working on is about doing global scale climate change detection attribution. And then I would like to end with some concluding thoughts about the collaboration in general. So the key science question of our project, as I said, it's about detection and attribution of climate change. So basically about trying to see in the data or to show in the data whether and how we see climate change signals. And to illustrate the key question we have in the DASH project is a lot about internal variability in the climate system. And I would like to give a short example about that. So these on these time series plots here, you see a couple of locations, and in black you see the observed temperatures in these places. So for example, Seattle, Washington, and then after 2010 you see a range of climate model simulations. It's actually from a 40-member ensemble, so from 40 different simulations with the same climate model, and plotted here is only the hottest member in red and the coldest simulation in blue. And as you see, they can show a very large spread between these two simulations just because of basically random chance, what climate scientists would say internal variability. So, and of course, this has been recognized a long time ago, and also in this paper, which basically implies that internal variability is puts some fundamental limits to climate projections simply because internal dynamics in the atmosphere. So one of the key questions for detecting climate signals is, can we actually improve signal-to-noise ratios of the climate signal and also the robustness for regional and global climate change detection and attribution using statistical learning or machine learning methods in our projects? And I would like to come to the first big topic we have been working on, and that's, as I said, it's about uncovering regional force climate signals. There's a method in climate science that had been out there for a long time, which is called dynamical adjustment. And the idea is basically that a lot of the variability, as you see here, in some target variable that one might be interested in, for example, precipitation or temperature in some region, is of course induced by simply random internal atmospheric circulation variability. So just could think of this as kind of weather variability or month-to-month variability that is, for example, in Europe, largely induced by how high and low pressure system basically are kind of aligned in space. And so this is a lot of variability that's just arising basically by chance. And then of course we can think of an external forcing signal like the climate change signal that that induces basically mostly a thermodynamic warming signal that's not directly related to the circulation. So climate scientists have been thinking for a long time, can we actually use circulation information to predict the variability in some target variable in precipitation or temperature? And then by basically looking at the residuals of this regression model here, would that give us kind of additional information about the forced thermodynamic change in some region? Or putting it in another way, does the kind of taking out the circulation signal, does it help us in interpreting this forced thermodynamic signal? Or it's kind of a noise, a circulation noise filter you could think of. And what we've been doing in the first year broadly of the project was to try a few statistical learning methods to make this prediction here from taking basically the spatial field of a circulation proxy, such as sea level pressure anomalies, and trying to predict target variables such as precipitation and temperatures. And then, but not in the interest of doing the prediction per se, but really interpreting the residuals and seeing if then kind of the forced thermodynamic signal comes out clearer. And our project is largely about changes in the water cycle, but of course, because in the atmosphere, signals and temperature are very, very strong and clear and also well understood. So that's why we tested these statistical learning and machine learning methods also for temperature related variables. So I will show some results for precipitation and for temperature. So first of all, you see on top here, basically for model simulations of winter precipitation change over North Europe. These are just in a 60-year period, just trend slopes of 30-year lengths that you would get by just kind of looking at the raw trends that come out of kind of different climate model simulations. And what you're seeing here, this is the gray box plot here. If you just take a 30-year trend slope over North Europe, over the last 60 in the period of the last 60 years, you actually see you can end up just by chance, just by random variations, with a relatively large kind of positive change or relatively large negative change, but just also kind of a large spread between the different simulations. Now, if we average across 21 simulations, which you see in the black box plot here, then the kind of the forced signal of climate change becomes clearer in these simulations just because the random variations average out. Now, if we do this dynamical adjustment method using a statistical learning method to use the circulation signal to predict the target variable, the precipitation, and then looking at the residuals, what we end up is actually just from one simulation, so comparing it directly to the gray box, but here we end up with a kind of relatively large reduction in the noise in these trend slopes, so a better ability to interpret these trend slopes. So the bottom line here is that dynamical adjustment using statistical learning method has really enabled us to uncover forced trends in precipitation and in temperature at the regional scale more accurately. So here it's just about having a higher signal to noise ratio. And then we made a short application on real world data, because remember, this was climate model simulation data. So we did an application on real world temperatures over Switzerland. We thought this would be interesting, first of all, because most of us live in Switzerland, but also because this time series of Swiss winter temperatures, so this is the cold season temperature in Switzerland, so from November to March. And what it's showing in black here is basically if you just kind of look at it naively in a sense, you would see that there's kind of this, what looks like a jump or some abrupt change here in the late 1980s towards higher winter temperatures in Switzerland. And this had been interpreted in the literature a little bit, where people talk about regime shifts and things like that. And if we do this prediction using circulation information of Swiss winter temperatures, we end up with the blue line here. So we get the kind of the year-to-year ups and downs in temperatures that are due to circulation. We can predict them very well, but we also see there's a certain uncoupling between the circulation-induced temperature and the observed temperatures in the last 30 to 40 years broadly. Now, if we look at the residuals, which you see as the orange line here, so it's the same time period, it's just the residuals, so the difference between the black and the blue line, we actually see that there's that first of all, the residuals are being smoothed because circulation information is taken out of the time series, but also that there's a kind of a relatively smooth trend kind of showing up over the last 40 years, which may include the climate change signal. So what actually looks like a jump here in the left original time series is if we kind of take a more statistical method to kind of separate circulation-induced changes and thermodynamic changes, is really a lot of variability induced by circulation, plus a relatively smooth, probably forced trend in the residuals due to thermodynamics. So again, this is just a short application of what we think dynamical adjustment as kind of a circulation noise filter that uses a statistical learning tool can do in order to improve higher signal to noise ratios for the climate interpretation. And just to conclude this first part of my talk, as an outlook, we have in these examples here, we have used a relatively simple statistical learning method for the experts that's called ridge regression and elastic net regression. So basically using a statistical penalty for a large number of correlated predictors. But of course, one can use kind of more state-of-the-art or more sophisticated methods, and we're doing this here in a follow-up work that's by a senior scientist called Christina Heinze-Demel at the Seminar for Statistics, where she is actually using kind of a state-of-the-art deep variational autoencoder to do essentially the same thing. So she's predicting here that's a high-resolution model simulation for precipitation. So you see, for example, the Alps here, the UK would be here, North Germany would be here. So where she's basically taking these kind of the original high-resolution precipitation simulation, and she's first of all reconstructing this with a deep neural net, and then she's using, again, similar to the plots I showed before, she's using the circulation information to get a prediction of this high-resolution simulation, which you see here for high-resolution daily precipitation, which we think is actually a quite nice prediction just by the sea level pressure response. All right, that was the first part of my talk. And I would like to come to the second part of the talk. So we have seen now at the regional scale, we can do a lot of things, dynamical adjustment to uncover trend slopes. But of course, there's still people saying things. If there's like a cold wave in the US, like 1.5 or 2 years ago, there are people tweeting things like, well, like the US president, for example, saying here, well, there's a brutal and extended cold blast that could shatter all records, whatever happened to global warming. But of course, what we have seen from my talk is that internal variability in the climate system is actually really large. And so we would, of course, always expect things like cold waves for a few days or a month or a season to happen. And so, of course, people were quick to point out that to Donald Trump here to say, well, climate is actually a global phenomenon. So this particular day where Donald Trump kind of stated, well, it's kind of cold over large parts of the US and North America, but actually, as a whole on the globe, the Earth on that particular day was 1.2 degrees above pre-industrial temperatures. And of course, we could have anticipated this even from the first slide of my talk, just because internal variability in the climate system is very large. So what detection attribution studies, so studies that try to look at kind of climate change signals, have been doing since basically 30 or 40 years, is to look at so-called fingerprints. So the idea here is exactly as this person stated here, to use not a regional signal, but a global signal and try to seeing climate change from the global signal. And because this kind of ends up being a hypothesis test in the end, what people are doing is basically the idea is to compare the physical model, so the expected warming as simulated by theory, so by our physical models, and to compare this warming against real world observations. So to have really a like-to-like comparison, but without any prior information from the real observations. So this is a method that has been out there for 30 to 40 years and is one of the cornerstones of the IPCC reports about climate change. So this basically works that people come up with a model simulation and have kind of the model's warming pattern, and this is what's being called a fingerprint. And then these fingerprints are being compared against model observations. So that could be a simple projection in the simplest case. And then the researcher would end up with kind of a signal to noise ratio in the end and the trend length of, let's say, 30 years or 40 years. And then one could come up with some sigma thresholds, which could be interpreted as p-values or things like that. So that's the simplest case. And the second big topic in our project was to come up with a more direct approach maybe for global detection attribution that basically uses that also uses this fingerprint. So the idea here was, instead of kind of coming up with this mean warming pattern, which earlier studies did, is to learn a fingerprint using a statistical learning or machine learning method from a pattern of climate variables, such as the spatial map of temperatures, for example, and directly predict a proxy for climate change, such as a long-term smooth temperature signal or directly the radiative forcing. And we're doing this here by basically minimizing a function that gives us coefficients for a temperature map that would predict us this forcing proxy. And then in a second step, we would take in observations and project these observations onto the fingerprints to end up with a test statistic. And so it's not that fundamentally different from the traditional fingerprinting method, but it's kind of using statistical learning methods kind of in a direct way. And what we did then was we did that for every single day. So we took reanalysis data and we projected every day onto these kind of fingerprint patterns from climate models. So what you see here in stronger orange colors are regions that project a lot onto the forced climate change signal. So regions that have a high signal to noise ratio. These are not by coincidence the oceans, particularly because they have relatively little internal variability and a relatively strong signal. That's why the oceans come up so strongly here, and the regions like Europe or the US come up relatively small, just because there's a lot of internal variability in the system. But the bottom line here is, once we do this learning step and then the projection of the reanalysis data onto the fingerprints, we actually end up with these kind of orange dots here. So every dot is kind of a prediction for a day. And what we actually saw is that we can actually, since about 2012, the signal has been moving out of the envelope of kind of historical variability. So this means that since about 8 years, we actually every day taken by itself would actually show the climate change signal. So earlier people were looking at kind of more longer trends, and of course they are kind of more significant in a way. But even a single day now is kind of strong enough from the signal to noise point of view. We have been doing the same thing with combining the temperature fingerprint with a humidity proxy, so including the water cycle here. And again, we come up with a relatively similar result, namely that climate change is basically visible now on every single day compared to kind of an early historical baseline. So I come to my almost last slide now. So just as to kind of mention this a bit from a science outreach point of view, we were a bit surprised or overwhelmed maybe by the kind of media response to this daily detection study. It might have been just because it's kind of a slightly different way to look at climate change from a kind of day-to-day perspective. But of course, it's quite nice that this scientific study reached a relatively large audience and was, for example, mentioned in the Washington Post or in National Geographic. All right, now just as a large outlook, just to say that this is certainly not the end. This is very much work in progress now. So we are trying to do not only detection. So remember here, we have just only shown we see the climate change signal, but we have not shown which particular forcing that is causing that signal. So we have not shown that it's CO2. We've just shown this is climate change happening here. So now basically we're working on a statistical method where we're trying to attribute changes in the system that we're seeing from the temperature pattern or from the precipitation pattern to specific forcing. So these specific forcings could be solar forcing or volcanic forcing, anthropogenic forcing. And so we're using here a statistical learning method that kind of takes into account that these different factors here could have some effect on the pattern. So what we need fingerprints that are kind of robustly predicting one forcing, but kind of protecting us against shifts on the other. So the goal here, and that's an outlook because it's work in progress, but the goal here is to have a good prediction accuracy even under change distribution. So even if one would intervene on the other forcings, that this prediction should stay robust. That's called distributional robustness in statistics. And the way we would be doing that is to not only minimize like the expected loss over one distribution, as we did in the detection example before, where we had only one forcing acting on the signal, but to minimize the error for a whole class of distribution. And there are kind of new statistical learning techniques around that are based on causal regularization that actually can do these things quite smoothly. All right, so I'm coming to my conclusions. The first part of my talk, we have been showing that dynamical adjustment can actually improve signal-to-noise ratios and then allow us to uncover forced regional trends in temperature and precipitation, or to have a kind of more accurate look at on regional trends, such as observed temperatures over Switzerland, for example. Then we have been using kind of a statistical learning approach on the global scale to look at kind of the global scale climate change pattern, and there it turned out that kind of we see from global weather now every day the climate change signal, which might not be surprising too much in the end to the climate community, but nonetheless, I think it's kind of a nice result maybe. And then as an outlook, so this causal regularization may help actually to increase the distributional robustness, or the robustness of these fingerprints, to actually pinpoint individual climate change drivers. And regarding our collaboration in general, I think what has been very kind of useful and fruitful to get the collaboration going was that we have got the time, or we had kind of got the time to allow to find a common language between more method-focused people and more domain science-focused people, which I think has been kind of fruitful in terms of collaboration. And right now, I believe there's kind of these methods have we're only scratching the surface here. So I believe there can be many spin-off climate science applications that might benefit a lot from the method development here. And this is what I had to say in my talk. So I would be looking forward to any questions. Thank you very much.
Okay. Thank you, Sebastian, for the talk and the clarity in the presentation. I have allowed all the participants now to unmute themselves and ask questions. I will do this in a self-regulatory way. So please feel free to unmute yourself and ask a question to Sebastian about about the work that you've been carrying out in the last 2 years. In the meantime, let me ask you a question about the new methodology. Why do we need this new methodology for the water cycle, and why the previous method wouldn't be good enough for understanding the changes, or if any, in the water cycle?
Thank you. Yeah, so the water cycle, of course, is quite, so many variables are of course quite noisy. So they have a large, I showed the internal variability mostly for temperature, but the water cycle even has a larger internal variability. So the noise is even higher. So that's why we believe that, especially for kind of water cycle targeted questions, these kind of methods that can kind of allow higher signal to noise ratios are kind of really useful. That's maybe the first part of the answer. And the second part, I also think that this causal regularization things here, where it's possible to kind of, of course, there are many variables that could could exert an influence here, and that we are not trying to kind of predict. So in that sense, these methods that allow in some way to put a causal constraint on a high dimensional pattern that might be kind of affected by many variables is also quite useful for the water cycle, because of course there can be many different factors that affect the water cycle, and in that way by extension also affect detection and attribution.
Okay, thank you. Matteo, go ahead.
Yeah, Matteo Spallanzani from ETH here. Very nice presentation, very clear. Just a question about, let's say, which was to you the most helpful contribution from the data science part? I mean, something that you as a domain expert did not was used to know or expect to apply. I mean, which were the innovations you encountered? Yeah,
I mean, there were actually many useful contributions. So thanks for the question, first of all. And so I think one of the main most useful things were kind of keeping this discussion kind of going most of the time. So I think that was kind of the most useful, even on a conceptual basis, because there was this constant kind of going back and forth with, is that actually, like, why are we doing this? Is there maybe a confounding factor involved? Do we need to kind of take into account potential confounding factors, and think like this constant kind of back and forth discussion, I think was quite useful because then it made kind of me personally be more specific about things. But then of course kind of the very obvious things like the technical implementation of things like these causal regularization techniques here, of course these are kind of the main things that we have been benefiting from this whole collaboration, so with the Swiss Data Science Center and also with the Seminar for Statistics, of course.
Thank you very much.
Okay. Do we have another question, or given the time, I think we will move on to the next block.